Today we're going to do some things with exponential and log derivatives. So I want to take a step back a little bit and talk about, by definition, limit definition for the derivative, why e to the x has the derivative that is itself. So we'll start with the limit definition for the derivative, and you'll recall from early chapter 3, f prime of x is equal to the limit h approaches 0, f of x plus h minus f of x all over h. Specifically for e to the x, this is going to look like e to the x plus h minus e to the x all over h. Sorry, don't forget your limits. Limit as h approaches 0. Okay. Now, if we let h be 0, on the top we'd have e to the 0, which is 1. I'm sorry, we would not. Take that back. We would have e to the x plus 0, which is e to the x minus e to the x all over h. E to the x minus e to the x is 0. H is 0. We'd have 0 over 0, which means this limit probably exists. It's not one of those where the limit doesn't exist. It probably exists. We need some sort of tool in order to find it. So the strategy here is going to be looking at the top. We need some sort of algebraic tool we can use. Anybody see it? Question is subtract the exponents? Kind of. We're actually, because both terms have an e to the x in them, we're going to factor that out, which does involve subtracting exponents. So I'm going to write this as limit h approaches 0 of e to the x quantity. This factoring gets a little bit weird, but if I divide e to the x plus h by e to the x, I'm left with e to the h. And I divide e to the x by e to the x, I'm left with 1. Okay? Now, I'm going to split that limit up into the product of two different limits. So I'm going to write it as limit h approaches 0 of e to the x times limit h approaches 0 of e to the h minus 1 over h. Now, we have two pieces here. We know the answer to this, don't we? It's the derivative of e to the x. E to the x. We're going to use that to our advantage in a moment. Okay? Do you have your graphing calculator, Sandy? If you don't, will you do that, please? Okay. So looking at these two pieces now, these two parts of the product, I have the first function doesn't have any h's in it. So the limit as h approaches 0 of e to the x is simply e to the x. The second part is a little bit unknown. We still have a limit that ends up with a 0 over 0. So what we're going to do is we're going to take a look at the graphing calculator in order to find that limit. There's a suggestion there. Will you take just a moment and put that into your graphing calculator, and we'll come back together and go on again. If you go ahead and put that function into your graphing calculator with x's, many of you already saw that the graph looks something like this, which kind of looks like e to the x, which might be a little bit weird, but don't draw too much into it because that doesn't matter that much. It kind of looks like e to the x though, doesn't it? Okay. We want to know what happens as x gets really close to 0. So we could trace, and we clearly, when x is 0, we don't know what y is. And we could trace here, but it's really hard to tell because we don't really have increments that are very good. So what I recommend doing is going into second window, which helps you set up your table. I like to start the table at 0 because that's the point I care about. I care about what happens when x is 0. And I'm going to set my table to have really small delta values. That's really, really small h values. And I want to see what the function does when x gets really, really close to 0. Good there? We go take a look at that table. We shouldn't surprise ourselves when we see those values. What is it approaching? 1, which we knew, right? Guys, we knew this had to approach 1 because it has to be e to the x times 1. Why? Because we were finding the derivative of e to the x, and we already have convinced ourselves that that is e to the x. We good there? Okay. Again, something you probably already knew, but I think it's worth kind of rehashing and doing a little bit of a limit definition for the derivative on anyway, because it's good to see that definition again. So, number one, for today, the derivative of y equals e to the x, we would say dy dx is equal to e to the x. Good? That's number one. We've already done it, though. We're going to use that idea to move into some a to the x's, and we're going to do some logarithm stuff as well. Okay? Next one is just a little bit of review on chain rule. And the question is, what happens if rather than an x up there in the exponent, what if I have a function? Does that change your process a lot? Not a lot. What is the derivative of e to the f of x? If it's an exponential function, if it's e to the, its derivative is e to the, so it's e to the f of x times what? F prime of x. What rule are we using? Chain rule. Okay? So take 10 seconds and do example 1. Go. Five seconds, no pressure. Everybody done? 10 seconds wasn't enough? Everybody done now? Okay. It's e to the. It's really important that you can identify e to the really quick. Now, e to the isn't really a technical term, but anytime the base is e and you've got an exponential function, your derivative, you always want to, at the very beginning, you want to write the same thing again. Now, what do I multiply by? 1 plus 2x. Okay, some of those things need to start coming a little bit quicker for you, if they're not yet. Good so far. I can put any complicated function I want in there as an exponent, and the derivative is still the same. That's why we like them. Okay? Now, we're going to move a little bit. This is kind of topic number 2. We did e to the x, now we're going to do a to the x. The thing to keep in mind here is that a is some constant. So what we're trying to do here is we're trying to come up with a universal rule that we can find the derivative of an exponential function regardless of the base. So it could be 2 to the x, or 3 to the x, or 4 to the x, or 10 to the x, or any other constant value in between. We're looking for a general rule for exponential functions. Keeping in mind that exponential functions have some sort of constant base and an exponent that is a variable, or, in the case of chain rule, that exponent can be a function. Okay? So, back in the day, well, not that long ago, pre-calc days, we know that e to the natural log of x equals x, right? Convince yourself of that. Why is that true? Why is e to the natural log of x equal to x? Tell your neighbor. Okay, whose neighbor came up with a really good idea? What is it? Ln is the same thing as log base e. Ln is the same as log base e, and if the base and the exponent are the same, because ln and e are, I'm going to make you use mathematical notation or mathematical language here, e and natural log are, starts with an I, inverse functions. E to the and natural log are inverse functions. So if I put a log into an e or an e into a log, I just get the argument back. Okay? So we are now going to write y equals a to the x in the form e to the natural log x. Okay? How might we do that? The shortcut would be we could rewrite y equals a to the x as y equals, how do I want to say this? Couldn't I do e to the natural log of a to the x? Would that be the same? Does that make sense? I'm just taking a to the x. It seems like a really weird thing to do, and it is a really weird thing to do. But I'm taking a to the x, and I'm putting it into a log, and then I'm putting it into the e to the. So I'm putting it into inverse functions. So have I changed its value? We haven't changed its value because I put it in composition of inverse functions. Okay? Now, there's going to be a trick here in a minute. And again, I said before, you don't ever have to do this again, but I want you to see it because it reviews a lot of the skills that we've deemed important. Okay? Now, if I've got the log of something with an exponent on it, how can I rewrite it? What can I do with that x? Remember this from pre-calc? I can put it in front. I can make it the coefficient. So this is x natural log a. Okay, which kind of leads to the next command on the notes. We know the derivative of e to those, don't we? If this is y, what's y prime? First, recognize that it is e to the, it's an exponential function. So write e to the x ln a. Now, what do I need to multiply by? The derivative of x ln a. It's written weird, but it's way easier than it looks. What is the derivative of x ln a? What is ln a? What is a? Hopefully you wrote it down. What is a? A is some constant. What's the natural log of some constant? Some other constant, right? More complicated, probably decimals involved, right? What is the derivative of x times a constant? Let me give you easy ones. What's the derivative of 3x? 3, how do you know? Because 3 is the constant multiplier on x, right? So what's the derivative of x ln a? Ln a. If I walk it through that way, it makes more sense, doesn't it? Okay. Do you ever have to come up with this again on your own? No. You don't ever have to come up with this on your own. Okay. Let's not even leave it like that, because there's an easier way to write this. Let's go back, and I know it's a weird thing to do, so let's go back and undo what we did that was weird earlier. What's this? What's e to the x ln a? A to the x. So y prime is a to the x ln a, which is kind of cool. We know that e to the x is its own derivative, and now we know that a to the x is really close to its own derivative, isn't it? A to the x is a constant multiplier away from its own derivative. Okay? It's a scale factor of itself, which kind of makes sense. You look at the shape of an exponential growth curve, or an exponential decay curve for that matter, and it makes sense that its derivative should also then be an exponential curve. So, will you apply this rule really quickly with me? Okay, let's do these quickly. What's the derivative? Now again, you don't have to derive the whole thing. Now, guys, it's a rule you memorize. What's the derivative of 4 to the x? 4 to the x, natural log 4. That's it. What's the derivative of 5 to the x? 5 to the x, natural log 5, right? What's the derivative of pi to the x? Pi to the x, natural log pi. Are there light bulbs going off for the next one? Mr. Best, we already know the derivative of e to the x, don't we? But if we use the rule we just learned, this is y prime is equal to e to the x times the natural log of e. Right? What's the natural log of e? 1. Isn't that cool? Okay, fine. I'm the math teacher. I'm the nerd. I think it's cool. You guys are just going to have to pretend it's cool and come along with me. Good? Eye rolls can continue. Tell bad jokes later. Okay, what about 5 to the x squared? Oh my goodness, can we do this? We probably can. What it really comes down to is it's just an exponential function with a function in the exponent, right? So y prime, bear with me, if it's an exponential function, it's its own derivative times a scale factor. With me so far? It's 5 to the x squared times the natural log of 5. There's another piece that I need to involve here. What is it? I need to multiply by 2x. Why do I multiply by 2x? Because it's the derivative of the inside. It's the Tootsie Roll center. Cool? A little? Okay. Are we there enough that we can just move on a little bit now? Isn't that fun? Guys, I'm going to skip method 2 right now. I don't think it's all that important because when I was looking around, you guys were like, oh, that's cool. So I don't want to mess with that. So we're going to skip method 2 because it's really just another method to get you the same silly rule. It's not a silly rule, it's a cool rule. But moving right along. Okay? Properties of logarithms. If you did that 3.9 day 1 stuff on Wednesday or over the weekend, you ran into some things that may have been a little bit complicated. I want to narrow this thing down. What you really need to know about logarithms, well, I shouldn't limit it to this, but the properties of logarithms you need to know are going to be narrowed down to 4. Okay? Property number 1, question. Test for this is next, well, let's see, Monday, Tuesday. Monday, Tuesday. The test will be, you can't really do a test on 3.6 just to 3.10. You it builds on the stuff before it. So it's really an all of chapter 3 test. Okay, really all of chapter 3. But keeping in mind that, what have we built on since we did 3.6? We did product rule, power rule, quotient rule, chain rule, implicit derivative, so it all kind of built. So it's Monday, Tuesday, individual Monday, partner Tuesday. Some of it. Some multiple choice, some free response. Yep. Okay. So 3 properties for logs. These are the 3 things you need to remember. Number 1, product. And I'll just use symbols. I hope you're okay with that. The log of a product, so I'm just going to say log of m times n is equal to log m plus log n. And I didn't put bases on there. I could put bases. I'll put an a for all the bases. Log base a. Log base a. It doesn't matter what the base is, guys. As long as you're consistent with the bases, you can add logs if you're taking the log of a product, and you can go back and forth across that equal sign. Second one, it involves a quotient. Log of m divided by n is as simple as log m minus log n. And again, the base doesn't matter. I'll put a's there. Whatever base you want, as long as you keep the base the same all the way across. Those look familiar? I don't want you to get confused thinking there's like 100 things you need to remember about logs. There's 4. Okay. Number 3 is a power. We already alluded to it this hour that the log of something like a to the m can be written as m times the log of a. And again, the base doesn't matter. Okay? The last thing that every once in a while, I don't know if you call it a property, it's more of a definition, but it's the change of base. And we're going to use that one in a couple of minutes, but the change of base tells you that if I have log base b of a, I can write it as a fraction, log a over log b, and again, the base doesn't matter, so you can leave a blank there. You can do them as log base 10, you can do them as log base e. Okay? How do you remember that the b goes on the bottom? Well, the b is the base, so the base always goes on the bottom. Relying on my incredible musical experience. A very versed composer of musical pieces. Or not. I think sarcasm is lost on the recording. If there's somebody from some other class not really getting the whole sarcasm in the musical realm for this, should I sing for them? Awkward moments on the video. That's what I'm going for, guys. All right. So if I were to boil down logs into those 4 things, we'd be in pretty good shape. And those are familiar, right? Okay. So moving right along, number 3 for the day. We are going to do natural log x. And you need a trick. And again, this trick you probably never need to duplicate again in your life. It's fun to know. When you become math teachers, you can do this for your students. Ready? Notice I said when. All right, so I'm going to take y equals natural log of x, and I'm going to use the definition of a log to rewrite it, solved for x. Do you remember how I can rewrite this so that x is by itself? How would you write it? y equals log base e of x. Does this help if I do that? How can I write it? E to the y equals x. Why is that true? That's the definition of a logarithm. Good so far? We haven't changed anything. We haven't done any calculus. Okay, we're about to, though. We're about to have some fun. You ready? Let's do an implicit derivative, shall we? Let's differentiate both sides with respect to x. You ready? Oh, this is going to be awesome, guys. All that turkey and stuffing and mashed potatoes and sweet potatoes and whatever else you had, green bean casserole, cannot remove implicit derivatives from your head. You ready? What's the derivative of e to the y? E to the y times dy dx. Why do we need a dy dx there? Because it's the derivative of y, right? Good. What is the derivative with... That notation's really messy now looking at it. What's the derivative of x? 1. Good so far? What would we like to solve for here? Dy dx. So we are now going to divide both sides by e to the y. And that doesn't make us completely happy because we don't like y's in our derivatives. We would much rather have an x in our derivative. Can we? What is y equal to? Natural log of x. So I'm going to take that y, I'm going to call it natural log x. So dy dx is equal to 1 over e to the natural log x. Oh my goodness. Could it be that simple? Dy dx is equal to... What did we start with? We started with if y is equal to the natural log of x, and we came to the derivative with respect to x of that as 1 over x. That's kind of mind-blowing. A little? Okay, you don't think it's as cool as I do, but that's okay. You will someday soon. What's the derivative of natural log x, 1 over x? Okay? Can I make it a little bit more complicated before we move on? I want to apply chain rule. I'm not going to make it a lot more complicated, just going to apply chain rule. Ready? Ready? I'm just going to do one. Let's do y equals the natural log of, let's do 2, because this could be fun. Let's do 5x cubed plus 4, and let's do a second one. Let's do y equals natural log of sine x. That's fun. What's the natural log rule tell us to do? This is not in your notes, by the way. I'm making these up on the fly. You okay with that? I want to apply them because I didn't think there was enough application in these notes. Okay, the derivative here, we'll go through it. Y prime would be 1 over 5x cubed plus 4. Whoa. Why? Because it's 1 over whatever the argument of the log is, times 15x squared. That's it, right? So simplified, this would be 15x squared over 5x cubed plus 4. Try not to simplify here, guys. You might end up crossing out something you don't really want to do. Cool? It's different. Why is it different? Because this is natural log of f of x, which means chain rule has to apply. So natural log of f of x, if I'm differentiating, becomes 1 over f of x times f prime of x. Sort of? This one's cool. Did you do this one already? Isn't that cool? Y prime is 1 over sine, right? Times the derivative of sine. What's the derivative of sine? Cosine. What's cosine over sine the same as? Isn't that weird? Like, I can't even explain it sometimes, guys. I think math is really cool. The derivative of the natural log of a sine of x, you can't even explain it. Natural log of sine, it's a composition of two weird transcendental functions, all of a sudden becomes a cotangent function. How cool is that? Okay, fine. I'm going to limit my excitement for the rest of this. I promise. Okay, sorry. Want me to go back? Where were we? Right there. Sorry, it's hard for me to contain my excitement sometimes. Sometimes I think math is just really cool. And I can't explain it. When you're not, the question is what will you tell your students? You will show your students these tricks when you are math teachers. You don't ever need to do these again unless you're a math teacher. Okay? All right. Okay, we've got two more quick ones. Two more quick ones, and then we're done, and we'll get you started on your homework. So we did e to the, we did a to the, we did natural log. Now let's do log base a. We're going to work under the same premise that we did last time we had an a. What is a? A is going to be what? Some constant. That's going to be important. Okay? Now the trick for this one is to start with a change of base. So y equals log base a of x can be written as a change of base with whatever base we want. What's our favorite base in the whole world? No, it's not 10. What's your favorite base in the whole world? The answer is e. Good answer. Thank you for playing along and doing 10. 10's a good base, but e is better. Okay? In Mr. Best's hierarchy of bases, e rules. We will write this as the natural log of x over the natural log of a. Because we haven't changed the function yet. We are doing pre-calc. We haven't done calc yet. Do we know the derivative of that stuff on the right-hand side, or do we need to do some implicit stuff? We could do implicit. Do you want to do implicit? You do? Let's not, and then I'll show you how the implicit would work. Okay? So this is the same as, and I'm not going to do any calculus yet. This is the same as 1 over the natural log of a times the natural log of x, isn't it? Do we know the derivative of natural log x? Yeah, it's 1 over x. Do we know what's a? A is a constant, so what's the natural log of a? Another constant, right? What's 1 over that constant? Some other constant, right? And what's the derivative of a constant times a function? The constant times the derivative. I don't want to I'm trying to follow a logical process, but I lost you somewhere along the way. Will you believe me if I told you right now that y prime is equal to 1 over the natural log of a times 1 over x? Okay, I made that more complicated than it had to be, but really it comes down to the fact that if you have a constant times a function, the derivative is the constant times the derivative. Okay? Trying to simplify it, but clearly I did not do such a thing. So really, y prime, if we started with log base a of x, y prime is 1 over, we typically write it as x natural log a. Okay? Somebody wanted at least to see it implicitly. If you want to do it implicitly, I started with this. I did it as ln a times y equals natural log x. And then I took that from here. And then you can do an implicit derivative from there. You'll end up with the same thing. Okay? Okay. Example 4. It's a race. I've got a Tootsie Pop for the first person that can answer example 4. Just say it out loud. Or raise your hand and say it out loud. What? It's not sine x. It's not tangent. Cosine x it is. It's cosine x. I wanna show you this really quickly. You're gonna be like, oh man, really? It is that simple. This is a log review problem. If I've got base a and base a, what's log base a of a to the sine x? Sine x. What's the derivative? Okay. Wasn't really fair. I made it a race and gave away a piece of candy, but you'll all be okay for it, won't you? You'll be okay. You've still got Halloween candy sitting in your house, don't you? Really? If your Halloween candy is not gone by Thanksgiving, it's a failure of a Halloween season, right? Guys, it's snowing. One last thing. Y equals natural log x. I'm done. I'm done anyway. Okay? Natural log x. Natural log x looks like this. Its anchor point is the point 1, 0. Its domain is the open interval 0 to infinity. Okay? In summary, guys, if you just cross this out quickly with me, it's not supposed to have that denominator. In summary, you should be able to pretty quickly, if not now, maybe by tomorrow, please by tomorrow, be able to find those derivatives pretty quickly. And in addition to that, I'd like you to also be able to do them with the chain rule. So e to the f of x, a to the f of x, natural log of f of x, and we actually did one of those, and y equals log base a of f of x. For tonight, I would like you to do day 2 homework from 3.9. I'll go back to that slide in just a moment. I would like you to know that day 3 on 3.9 is optional. I handed all of you a white sheet. It's not a terribly complicated process. It actually gets you out of some nice jams, but it's not an AP AB topic. It's logarithmic differentiation. If you look at this little white sheet helps you get through the last 3 or 4 problems on the homework, which means the last 3 or 4 problems on tonight's homework are not required, but I think it's a nice little process if you have time to do it, and if you don't have time to do it, I'm not going to be mad at you. Okay?